Okay, so section 9.10 is on Taylor series or Maclaurin series in the special case where our series is centered at c equals 0. Okay, so this is going to generalize the idea of Taylor polynomial. Okay, if you recall, the Taylor polynomial was a polynomial that approximated a function at a particular, centered at a particular point. Now we're just going to take those Taylor polynomials and extend them infinitely. So we'll have an infinite polynomial, which is called a Taylor series. So the definition of the Taylor series is, well, first of all, we need to have a function that has derivatives of all orders. So I'll say that if a function f has derivatives of all orders at a point that we're centered around, which is x equals c, then we have that the Taylor series is a series from 0 to infinity. We take the nth derivative evaluated at c divided by n factorial times x minus c raised to the n power. Okay, and so if we look at the first term of the series, it is, well, if n is 0, we just get f of c. If n is 1, we get f prime of c times x minus c. And then if n is 2, we have the second derivative evaluated at c divided by 2 factorial times x minus c squared plus dot 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 plus, and now we just take the nth derivative evaluated at c over n factorial times x minus c to the n power. But we would end here if we were computing the nth Taylor polynomial. Instead, we just say plus dot 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 and continue to infinity. So this is the Taylor series for f of x at c. If c is 0, then we call this a Maclaurin series. So a first example. Very simple example is f of x equals cosine of x and c equals 0. So we're going to find the Taylor series or the Maclaurin series for cosine centered at c equals 0. And so it's a matter of taking derivatives and computing them at 0. And so this is easy for cosine, because f of x is cosine, f prime of x is minus sine, f double prime of x is minus cosine, f triple prime of x is sine. Fourth derivative is cosine. And as you can see, we would be cycling through the sine and cosine if we took more derivatives. So, and I'll actually just write down what the fifth derivative is. Of course, it's minus sine. And what we want to do is we want to evaluate these at 0. So, well, f of x at 0 is 1. F prime at 0 is 0. F double prime at 0 is minus 1. F triple prime at 0 is 0. The fourth derivative at 0 is 1. And the fifth derivative at 0, of course, is 0. Okay. And you could imagine what the sixth derivative, and I mean we can write down what the sixth derivative is. It's minus cosine. And of course, if we evaluate the sixth derivative at 0, we get minus 1. So you can see a pattern building up in the evaluations of these derivatives. 1, 0, minus 1, 0, 1, 0, minus 1, 0, and so on. So now, using our Taylor series formula, we have that our f of x is equal to, well, f of 0, which is 1. F prime is 0, and so there's no second term here, but there is an x squared term, and that x squared term is minus 1 divided by 2 factorial times x squared. Alright, there's no x cubed term because the third derivative evaluates to be 0. The fourth term is, well, positive 1 divided by 4 factorial x to the 4. There's no fifth term, okay, because the fifth derivative is 0, but the sixth term is evaluated as minus 1, and minus 1 over 6 factorial x to the sixth, and then plus, we would get more terms, dot, dot, dot. So this is the Taylor series for cosine. And if you look at it, it's composed of all powers of x that are even, and of course a constant, but a constant can be thought of as x to the 0. So for Taylor series of cosine, all of the powers of x are even. And so this should make sense that cosine is an even function. And finally, what we can do with this formula is to write down what the series is in a nice notation, and we can write that cosine of x equals summation from n equals 0 to infinity. Now, is there a pattern that's been established here that we notice? Well, you certainly see that there is an alternating sign here. So I'm going to write that there is a minus 1 to the n, or n plus 1. You can think about which one that is. If you notice, the first term is positive, so if n is 0, we want minus 1 to the n, so that we get a positive. And then what? If n is 1, of course we get a minus sign, but we want to get an x squared divided by a 2 factorial. So here, notice that well, since we're skipping terms, we need to put an x to the 2n and then divide by a 2n factorial. And so this is a nice representation of the cosine function.